Do you understand? This bamboo becomes a sword.
The Terminator, released in 1984 and directed by James Cameron, featured groundbreaking visual effects for its time, particularly in its depiction of the Terminator's vision. The Terminator's vision in the movie is presented as a heads-up display or else HUD overlaid with various data readouts and targeting information. This effect was achieved through a combination of practical effects, miniatures, and post-production techniques. The visual effects for the Terminator were crafted using early computer technology available at the time. The specific computer systems used during productions are not widely documented, but it's likely they utilized systems available in the early 80s, such as the Amiga, Apple II, or early IBM PCs. The software used to create the Terminator's vision was custom-made for the film. It involved a combination of computer-generated imagery, CGI, and traditional animation techniques. The Terminator's vision is depicted with a distinct red-tinted color scheme and a digital overlay of information. While specific assembly code isn't explicitly shown or referenced in the movie, the visual style suggests a futuristic and technologically advanced system. And while the Terminator's vision's code is not shown in its entirety, we are able to trace back the origins of the graphics. The software can be found in Nibble magazine's September 84 issue, which has most of these graphics. The compass is merely an educational tool, a quiz written in Apple Basic. The program uses high-resolution graphics to help youngsters learn the points of the compass. This scheme is just an impressive graphic design that portrays the graphic capabilities of the Macintosh computer. Paint Patterns is the name of that article. The article is about MacPaint. It explores the Mac's quick draw routines with an in-depth discussion in order to create advanced graphic patterns for the time being. The code that you see listed on the left is 6502 machine code and is nothing more than a random hex stamp from the Apple II computer. The code at the right is 6502 unassembled assembly source code. We know that it is not assembled because it includes the comments of the programmer. When you compile assembly code, the comments vanish. They are not kept in the output file. And that is one of the main reasons that reverse engineering is so difficult. When you reverse engineer assembled code, you can't tell if what you see is data or CPU instructions. That would be clear if the comments were saved in the assembled file, but they are not. For instance, while trying to reverse engineer code, you might see a typical return instruction of which the opcode is 60, and that 60 might not be the return call. It might simply be data represented with the same number. We use the word monitor to refer to a system command prompt that has to do with directly accessing and managing the memory. The Apple II system monitor starts at FF69 hex, 65385 decimal, or minus 151. And in case you wonder, how can we possibly have the same result with two different numbers? The answer is because in the computing world, a numeric value can be defined with more than one ways. A numeric value is signed if it can represent both positive and negative numbers, and unsigned if it can only represent positive numbers or zero. And that depends on how we instruct the CPU to translate the sign flag. For instance, if we have the 4-bit unsigned binary number 1111, we can translate it to 8421. Or if we have the same but now signed 4-bit number, we could say that the first bit is a sign symbol, a plus or a minus, a plus when bit 1 is set to 0, and a minus when bit 1 is set to 1. So in that case the number 1111 is not 8421 anymore, but minus 421. To enter the monitor, you simply call 65385 or minus 151, and that gets you in the monitor screen. If you type 4000L the monitor will dump the contents of memory location 4000 hex, making an effort to disassemble them from machine hex code to assembly code. The code that you see here is once again 6502 code specifically for an Apple II. The tail here is the AUXMOV. AUXMOV was a routine in the ROM that moved data blocks between main memory and auxiliary memory. It works similarly to the ROM routine move, which was in the Apple II from the very beginning, and copies memory within a single bank. This code appears to be from an Apple II DOS 3.3 RAM disk driver, a popular way to use the auxiliary RAM bank with programs that couldn't use the auxiliary memory for anything else because it didn't exist when they were written. VTOC is a term used by both the Apple II and the Atari DOS, and that's not a tell in itself. However, given that we know that it's Apple II program from the AUXMOV, VTOC does indicate that it's an Apple DOS 3.3 program, rather than a Pro-DOS program. Pro-DOS doesn't use the term VTOC, but rather uses volume bitmap. The majority of shots through the Terminator's vision show a dump of the ROM's code for the Apple II operating system. Also, other parts of the code visible were written in COBOL. Another code we see here in the Terminator's vision is the keyperfect4, a source code error checker to prevent crashes. The Terminator's vision effects were groundbreaking for their time and have had a lasting impact on the sci-fi genre. The film's depiction of futuristic technology, including the Terminator's vision, has influenced countless other movies, TV shows, and video games. James Cameron and his teams were more than visionaries. They were true pioneers and game changers.